Now let us look at some technological issues in the fabrication and characterization of photonic integrated circuits. So broadly this is the outline of the presentation. We will look at materials and technologies that are involved with the various processes that we can use to make these photonic integrated circuits, and then we will take up some specific fabrication processes. I have chosen 3 processes for 3 different applications. One is a glass based process, and the other one for dynamic devices, and one for silicon based devices. So, if you look at the various materials that are useful for photonic integrated circuits, the most common ones are as follows. So, the most prominent optical materials are glasses. They are very transparent in both the visible and infrared frequencies, but they do not have any active properties. So, they could be used to make passive devices like branches, couplers, waveguides and so on and so forth. Then of course, there are the lithium niobate is a crystal. There are many crystals which have got very useful properties like electro-optic property and so on, and they can be used to make dynamic devices. But some of the important problems with the lithium niobate are the drift due to variations in the material properties, etc., which is not very desirable. So, the stability of the material and the device properties is an important problem, that is a negative point of that. And as we know, silicon is the most prominent material for electronic devices, and it is one of the important candidates for photonic integrated circuits also. And the domain is called the silicon photonics, and you can make optical devices and photonic integrated circuits compatible with CMOS devices. But of course, it is not an active medium, which means that there is no electro-optic effect or magneto-optic effect or other things. So, you cannot control the properties of the devices externally, but of course, it has got very good optoelectronic properties. You can make detectors, and more importantly, silicon has become a very important material system for MEMS applications. So, you can make a lot of mechanical devices. It has got very good mechanical properties. So, you can make mechanical devices on silicon, and of course, if you couple or combine passive photonic integrated circuits with silicon, you can make very good optical MEMS, so to say. In a future talk, we will be looking at what are called optical MEMS or MOEMS. So, this is another important reason why silicon has become important. And of course, looking into the future, we need compound semiconductors like gallium arsenide, indium phosphide and so on, and combinations of that. Gallium arsenide, indium aluminum arsenide and so on. The 3-5 materials are very important because they have a direct band gap properties, which means that we can make very active devices with that, like laser diodes can be made with these materials. And of course, the technology is growing, and in future it is possible that we have electronic devices also compatible and with good, of course, in addition it has got the properties, active properties like electro-optic properties and so on. So, they appear to be one of the most promising candidates, but the only limitation at this moment is the technology is expensive and limited as compared to silicon. There are a lot of other materials like polymers, which are important candidates for many applications, particularly from an application point of view. Polymers and biomaterials and many other materials are useful as candidates for photonic integrated circuits. So, these polymers of course are slightly lossy, that is a negative point, but they have they are very cost effective. Sometimes they have good properties like electro-optic effect and so on, and the fabrication process also sometimes are very simple. So, polymers also are going to be one of the important materials, and other material systems that we can also have a look at, or for example, the magnetic materials, if you want to make magnetically active devices like what we have seen earlier, polarization controllers and so on. Then there are specific materials which are useful for SAW device applications. If you want to use surface acoustic waves, you can use, of course, lithium niobate is one of the candidates for SAW applications, but you can think of materials which have got very good acousto-optic effects. And also we need to think of materials which can be deposited over the standard materials to create more devices. For example, if you would like to make a biosensor, we can have a silicon device over which you can create cladding layers over that, and we can use them as biosensors. So, we need to deal with additional materials like biomaterials in as a technological, from a technological point of view. So, let us look at some of the various technological processes that will be useful for fabrication of these devices. The first, the preliminary description is in terms of a broad range of technological processes. Then we look at more specific issues. As you can observe that these are adapted or improved from the existing technologies of CMOS and thin film and thick film processes. So, I am showing a few technological issues which can be grouped under what can be called as lithography. Lithography is a process used to transfer a given design or pattern onto the wafer or a substrate. So, if you have a mask pattern, or if you have a design of a structure like this, for example, one of the important steps involved in the fabrication of this device is to start with the design, and then we have to translate onto the wafer. First of all the pattern, then comes the other process like diffusion or etching. So, if this is the top view or cross section, we have to transfer on the one of the layers. So, we have to transfer this pattern onto the wafer. This is only a pattern. Later on it will be either etched out or diffused. For example, I may etch out all the unnecessary portion to make a ridge waveguide on silicon. So, the process of transferring this design pattern onto the wafer can be called as lithography, and it is a very important process, and it may have to be used repeatedly to realize the device. For example, if there is an electrode to be deposited or patterned on the waveguide or adjacent to the waveguide, we have to use lithography once again to make the electrode pattern. So, there are various lithographic mechanisms in practice. So, they can be categorized under top down approaches and bottom up approaches. So, you have optical lithography where you use light waves or ultraviolet light waves to transfer this pattern onto the wafer. Then this is a technology which is well suitable for mass production, but the resolutions are limited by the wavelength of light that is used. The resolution limit is described in terms of the size of the features that you can get with respect to the optical wavelength. So, similarly we can use electron beams for as a lithographic patterns, and you can call them as the process is called the electron beam lithography. Instead of using the light waves, use electron beams, and you can find out the energies of the electron beams and their operating wavelengths, wavelength of electron. So, it is also known that electrons can also be considered as waves, and we can define a wavelength for electron based on the energy of the electron beam. For example, if E is the energy of the electron given by the charge, if you accelerate an electron beam through a potential difference of V volts, you can say that it has got the Q into V is the energy, and if you say that it has got a wavelength of, and of course we know the mass of the electron. So, we can say that we can determine the wavelength of electron. So, if the speed is v, mv is the momentum and half mv square is the velocity, and we can determine the wavelength of electron beam. So, once again the feature size that can be obtained is of the orders of d by lambda, and which is much smaller than the wavelength of electron is much smaller, of the orders of nanometers, or so this optical of the orders of micrometers. We can calculate the wavelength of electron, which can result in very high resolutions, and it is a serial process. You do not have a mask, but point by point you write the pattern, and it is a slow process and is not very suitable for mass production. Similarly, you have other processes like nano imprint lithography, which is a repeatable process and is suitable for mass production. It is quite simple. Similarly, you use multi-photon lithography, similar to other electron and optical beam lithographies, where you use several photons. Interference of these photons can result in very good beams which can be used for lithographic process. Similarly, there is what is called a scanning probe lithography, where you scan the entire pattern and then write wherever you would like to have the pattern. The other processes which can be considered as a bottom up type of process are thin film processes. You need to coat a thin film uniformly and then use the lithography to pattern these devices. Sol gel is a process where you have a combination of titanium dioxide and silicon dioxide in the form of a gel, and which can be applied on top of these substrates to and then later on pattern it using the above lithographic processes. So, there are several tools for fabrication. They are categorized as the thin film processes like vacuum evaporation, the sputtering, the chemical vapor deposition, electron plating, and then epitaxial methods like molecular beam epitaxy and so on. So, the etching processes are used to etch out unwanted regions from the wafer. So, suppose you want to create an optical waveguide, there are regions where optical guidance is required can be retained and other regions can be etched out. We have already seen that lithographic processes are needed for patterning. So, let us quickly look at the operation of lithographic process based on either optical E beam lithography. You have to transfer a pattern to the substrate and then use etching, dry or wet etching to create these patterns. So, this is a simple process starting with the pattern transfer and then etching. These are the two important steps in the lithographic process and realization of the device. So, slightly more some more details about the lithographic process. The optical lithography basically consists of using the ultraviolet light to expose a photoresist which is coated onto a substrate. So, you start with a substrate, then you have a device layer like for example an oxide into which you would like to create the layers, and then use a photoresist and expose the photoresist through the mask. So, typically an ultraviolet light is used to expose this photoresist. On exposing to UV light, the photoresist bonds of the polymer break and they will become amenable to removal or etching. So, you have different types of photoresists. There are what are called the positive photoresists, which result in a pattern on the wafer which is same as that of the given mask, and there are negative photoresists where opposite happens. So, negative photoresist on exposing to ultraviolet light leads to creation of the bonds rather than the breaking of the bonds, and so the pattern can become the opposite of what is realized. So, in optical lithography the feature sizes resolutions are limited by the wavelength of operation, typically of the orders of a few hundreds of nanometers. This is ultraviolet light. See, in electron beam lithography, we do not have a we need not have a separate mask, but you have a photoresist which is sensitive to these electron beam energies. So, you have the substrate, then the device layer and quite a uniform layer of photoresist, typically by spin coating for example, and then expose. You have a design pattern in a computer for example, and then directly the electron beam can expose the pattern, the photoresist to the pattern. So, that is one of the important recent developments where you need not make a separate mask for exposing this photoresist. Once again you have positive photoresists or negative photoresists as we discussed for the optical lithography. So, the resolutions possible are of the orders of a few nanometers. So, let us look at a few device fabrication process. So, illustrated here is an ion exchange process which is a typical as an example for glass optical waveguides. You have a you can make waveguides in glass by using the ion exchange process. So, this is the device that is desired at the end, and you start with a glass substrate. Typically it has got, say if you think of a soda lime glass, you have got a sodium ions, you got a positive photoresist and you expose the photoresist through a mask to ultraviolet radiation, and you create a, in this particular case we create a trough region like this, where this can be called as protective region is retained except in this region where you would like to create the waveguide. So, then you have a bath of diffusant and you melt it if necessary. In this particular case have a nitrate malt, for example silver nitrate in a container, you melt it to a certain degree whatever you require, and then you dip this entire wafer into that. You place the entire wafer into the melt and allow it to diffuse. So, you have the, in specific case the sodium ions of the glass can diffuse out, and rubidium or silver ions can diffuse into this through this. So, this is called an ion exchange process. That is how it is called an ion exchange process. Silver ions or rubidium ions are exchanged for sodium ions. So, finally leading to a, and of course in the end we need to remove, to etch out this protective layer, resulting in a device configuration that is required. So, you may note that this results in a gradual diffusion of the materials into the substrate and may result in a graded index waveguide. So, the refractive index profile for a typically diffused configuration is graded index. This is a very simple process, it does not need very complicated clean environment except for the lithographic process. The diffusion could be done in a slightly lesser low environment, and is very commonly used for making passive optical devices in glass. So, typical temperatures are of the orders of a few 100 degrees centigrade for about 8 hours, or maybe let me say in the case of glass waveguides you can go for 1 hour, less than 1 hour. So, it is not a very complicated process compared to others that we will see later on. And diffusion times typically are of the orders of a few hours, few minutes to few hours. Concentrations necessary are of the orders of a few percentage, and the refractive index difference, the refractive index contrast that we can obtain depends on the concentration of the silver that we diffuse, typically of the orders of percent, a few percentage, 1% change in the 1% diffusion, one concentration of 1% can typically lead to about a few percent change in the refractive index. That is orders of magnitude that is possible with ion exchange process in glass. Next we look at another important process that is also commercially important and well established, is called the diffusion process. We are taking the example of a lithium niobate device into which titanium element metal can be diffused to create very good optical waveguides. So, you can make titanium diffused waveguides into lithium niobate. So, this is the configuration that we have. You start with a substrate of lithium niobate. This is very commonly used for titanium diffusion to lithium niobate. Start with a substrate, you have a photoresist, positive photoresist uniformly coated on the lithium niobate by either a spin coating or some other process, and then you have a mask and expose the photoresist to ultraviolet radiation. Then of course, we have to develop this photoresist, and then you deposit a layer of titanium. This is a titanium film over this. We observe there is a, so due to the development and the lithographic process, there is an opening in this region, and titanium is deposited only in the region where we need. So, after you etch out or lift off, the process is called the lift off, all this photoresist and titanium unwanted titanium film can be removed, resulting in a small titanium film on the lithium niobate substrate. This is of the orders of a few hundreds of angstroms. So, now this process is called thermal diffusion. You put it the wafer in a furnace controlled with a controlled temperature control, and then allow it to diffuse. So, the final result is an diffused optical waveguide like this. Once again, this also results in a gradient index optical waveguide in lithium niobate. And we have already seen earlier that we can make active devices in lithium niobate. For that, we need to deposit additional layers. For example, in this case, you note a electrodes adjacent to the waveguide. So, this is a negative electrode, this is a positive electrode. You can apply electric fields and change the refractive index properties of this lithium niobate. So, using a process similar to depositing the titanium film, you can deposit a metal electrodes, either gold or titanium or whatever suitable material. You can create electrodes. This is a two-step process. In the first step, we have deposited the titanium and diffused, and in the next step, you created electrodes. So, typically the parameters for the lithium niobate process are about typically 8 hours up to the 1000 degrees centigrade, and the concentrations once again are of the orders of a few percentage. 1% change in the refractive index, 1% change in the refractive index is sufficient to make very good optical waveguides. Once again, we have result in the gradient index configuration for this. There is another related process I can mention for the lithium niobate devices called a proton exchange. Where we use hydrogen ions to diffuse into lithium niobate, and so we take a melt of, like what we observed for the glass waveguides. You take a molten benzoic acid which contains hydrogen ions, and they could be diffused into the lithium niobate. So, this proton exchange process is at a low temperature, and it could result in almost step index waveguides. So, this could be done at a room temperature. So, another important process that is used in practice is called the silicon photonics. The subject is called the silicon photonics, and in this particular example we are illustrating etching of the materials or different layers that is deposited on the silicon wafer, creating optical devices combined with MEMS structures. So, MEMS structures are mechanical structures, as we may see later on in the future talk, future discussion. You can combine MEMS with optical waveguides to create what are called MOEMs. So, in this example we are showing a device which has got a cantilever beam. This is a cantilever beam on silicon wafer, and also the optical waveguide on the same substrate. You have a silicon wafer and then adhering oxide layer, and on top of it you have other layer of silicon into which you create waveguides and mechanical structures. So, this is a typical structure used to illustrate the silicon photonics. You start with the silicon wafer, and you already have an oxide buried inside the silicon, and there is one more layer of silicon on top of this, silicon, oxide and silicon. So, the wafers are available in this configuration, in the SOI configuration, silicon on insulation, silicon on insulator configuration, substrate is silicon. Then you pattern it using lithography process. Start with the positive photoresist using electron beam to create patterns in this, and after development you retain only the photoresist in the unwanted regions and openings in the regions where you would like to etch. So, the process called dry etching is used to etch out the silicon device region. See, this top silicon layer can be called as a device region, the silicon. So, the silicon of the design, the device region can be etched out by using what is called this dry etching process. There is also what is called a wet etching process, where you use a liquids to etch out chemicals to etch out the materials, and you can also etch into the wafer. For example, in this particular case you are seeing that using this opening you etch out oxide in this region. So, this is possible by using the chemical wet etching, and the structure remains on the top of it. So, here we are observing a cantilever beam being released at this point. So, of course, by using the other the etching process you can etch out the top photoresist layer, resulting in the given structure. So, this is a process. In this particular illustration we are showing a process where you make optical waveguides, ridge optical waveguides on silicon along with a cantilever beam. So, let us look at a few techniques for measurements and characterizing these integrated optical devices. So, the most common techniques involved in measurement of integrated optical devices in a laboratory consist of using a laser source, sometimes tunable laser source depending on the properties that you would like to mention, and devices for polarization control, and the XY stages to position the input beam with respect to the photonic integrated circuit, and then finally a detecting system like a spectrum analyzer or a photo detector to measure. So, the basic photonic integrated circuit is placed on a platform like this and excited with an input optical beam coming through an optical fiber. Typically, the optical fiber itself, as you know, has got a refractive index or a cross section, circular cross section of 9 micron, and the typical integrated optical waveguide devices have dimensions of the orders of 0.5 micron by 0.25 micron. So, on silicon, typically on a typical silicon waveguide you have half a micron by 1/4 micron, which is very small compared to the dimension of the optical fiber. So, a lensed fiber is used to focus light onto this. Even then you have a circular mode spot which may be slightly more than this. So, there is a mode mismatch between the input light and the mode of the optical waveguide. This is one of the important feature or characteristic of the measurement process. So, we need to have mechanisms where we can inject light into this integrated optical device very efficiently. At this moment we are considering the characterization, where we would like to measure the properties of this device like loss of the waveguide, then the mode field properties and so on and so forth. So, in case we want to study the properties of this waveguide with operating wavelength, then we need to have a tunable laser source, and an optical spectrum analyzer is a very versatile device which can be used to display the whole spectrum of light that is coming out of this. Otherwise, it is also possible to have a conventional screen to image the beam coming out of this. For example, we can observe the mode spot on a screen and correlate this with the properties of the modes in the optical waveguide. So, this process is called edge coupling, where we are launching light from an optical fiber onto this. These XY stages are very important and are useful to position this accurately with respect to the center of the waveguide. So, the resolutions required are of the orders of a few nanometers. Nanometer alignment tolerances are needed. Using this lensed fiber, we can focus this beam onto of the orders of a micron. Still it is bigger, still it is bigger than the waveguide mode spot. So, we need to have alternative mechanisms to match the mode with the waveguide beam. Mode matching is what has to be done. Matching of the input field with the mode. So, this is another new process which has become important recently, called the grating couplers. You on the same wafer where you have the optical circuit, this optical circuit required, you create waveguide gratings. Waveguide grating, as we have seen, is a periodic variation of the refractive index, and it is possible to work out when a light is launched from an optical fiber onto the grating. The light could be just coupled into the optical waveguide. So, the light coming from an optical fiber falls on the grating and couples into the photonic integrated circuits. We also note that there is a tapering region. So, if you have mode spot side of a micron and waveguide width of half a micron, we need to use a tapered waveguide to gradually launch the light into the optical waveguide. Once again, you need the other optical elements like the polarization controller, the XY stages, a spectrum analyzer, and so on and so forth. If you want to measure a loss of the waveguide, for example, we can consider fabricating different lengths of the waveguide on the same substrate, and say for example from here to here is one. I will make another smaller waveguide, and the loss differences can be measured. For example, this is an extra length L and L dash, this is L and this is L dash. So, the extra length, the propagation loss for the extra length will be estimated by measuring the output optical power. So, there is in a laboratory there is another very simple and useful technique called M-line experiment to assess the properties of the integrated optical waveguides. This is more particularly useful for characterizing the fabrication process. So, an important requirement in the development of the photonic integrated circuit is the fabrication measurements. Until now we have seen the measurement of optical devices. It is necessary to estimate and measure the fabrication conditions. Fabrication conditions could be very well estimated and measured by using slab waveguides. For example, we would like to measure how much is the diffusion depth and what are the concentration and how it behaves with respect to the fabrication conditions like temperature, concentration, time of diffusion, and so on and so forth. The M-line experiment or the prism coupling experiment is a method to launch light into a slab waveguide and launch these modes. We can excite the modes of the slab waveguide. All the modes that are possible to be propagated in a slab waveguide can be excited by using this prism coupler. Here we at this point where the prism is located, at the base of the prism, we apply small pressure by using a tightening mechanism. So, the gap between the prism and the waveguide can be adjusted, so that by evanescent coupling the light incident at the base of this prism can be tunneled into the optical waveguide, slab optical waveguide. In a similar reverse process, the light could be ejected out of the waveguide through this prism by controlling the gap between these. So, by measuring the field output or the angles at which the light comes out, we can estimate what is the propagation. So, the angle of exit can be related to the angle of light that is propagating inside the optical waveguide. So, if there are several modes propagating at different angles in the film, we get output at different angles. So, each one can be said to correspond to a different mode, and we can put the entire thing on a spectrometer stage and rotate this such that you can measure any specific angle of the mode that is propagating, and you can correlate with the properties of the optical waveguide.